So so these are based on lectures. Okay, based on lectures by Pedro Vieira. So you can find them online. It's based on his lectures, and we'll try to understand the gist of basically the gist of graph theory and some random matrices. Okay, so let's start. Say we have a two-dimensional random surface. It can be a membrane. It can be, let's say, a membrane between two different liquids. It can be a membrane in a statistical mechanics problem or biology, or even in string theory, it's called worldsheet, but that's not important. So 2D random surface. So they are related. So say we want to explain the two-dimensional random surface. How do we do that? One way is we can fill this random surface up by triangulations. So we can fill this up by, say, triangulations.
Could I ask a question?
Sorry?
Could I ask a question, please? I mean,
yeah.
So could you please define what do you mean by random surface?
Let's say you have a two-dimensional surface, and it can be any sort of any shape or any it can be of any shape. It's just a two-dimensional surface.
So like just an arbitrary surface.
Exactly. Exactly. An arbitrary surface. If you have questions, just interrupt me and ask. So let's say we want to explain the dynamics of this surface. Our end goal will be that. But let's say we want to explain the surface. One way we could do is we could break them up into, let's say, triangles or polygons. So we could make a discrete version of this. Let's say discrete version of this graph. Discrete version of this random surface. Discrete version we could make, let's say we could have triangles or polygons or different sizes, different things. Let me have it. Yeah. So the main idea is to explain this random surface, and what we could do is discretize this surface. So if we discretize this, and if we explain the discrete part and take, let's say we have infinite number of such discretized graphs, and then we can explain the two-dimensional surface. So these discrete graphs are in the domain of something called graph theory, which may be very familiar to our computer science people. So they could be different graphs. Some are vertices, they are edges. We'll go to that. So the basic idea is, if we want to explain the two-dimensional surface, we discretize this and make it in terms of, let's say, polygons or triangles, and we want to explain how this surface works. So for this, we'll learn two things in this live lectures. One of them is graphs, which we will see today, and probably the next day we'll see something called maps. And I'll define this later. Just stick with graphs for now. So graphs are very much related to Gaussian integrals, which we will see today. Graphs are basically, let's say, triangles or polygons or whatever. So graphs are related to, say, Gaussian integrals over numbers. And for maps, we will see what these maps are basically graphs with a bit more structure, which we will see the next day. For now, just for now, just think of it like graphs with some extra structure, which we haven't defined now. And maps are Gaussian integrals. So let's write Gaussian integrals over matrices. So this is how matrix models came up. Like the idea of matrices is a way of taming these maps. It's like, for example, the discretized version will be explained by Gaussian integrals over numbers. And the maps will be explained by Gaussian integral over matrices. Okay. All of these ideas came just to discretize our two-dimensional surface. Okay. Now, let's look at some simple possible graphs, because I've been saying graphs and graphs, but we haven't actually noticed any graph. So let's first start with the simplest possible graph. Simplest possible graph. Okay, let's say we have one vertex and this thing at the center, it's just the lines coming out of it. We call this a vertex. And we call this graph of valency 8 because you can see 8 lines are coming out of it. And let's see, what else do we have of a graph? Okay, we have the edges. And 1, 2, 3, 4, 5, 6, 7, 8. Let's say we contract them or join them like this and make a flower-like structure. These are called edges. The lines that connect to one another. These are the edges, these are vertices, and the lines coming out are, let's say, valency. If you have any questions, you can ask me at any point. Just make me stop and ask. So this is one simple graph of, let's say, one vertex graph. What about, let's say, if we have two vertices, let's call this A. Let's see if we have two vertices. We can have a graph like this. It's just two vertices are joined. Can someone say how many oh, okay, I said it's two vertex. How many edges are there for each vertex? Can any of you say how many edges we have here? So edges.
3.
For each of them, notice how we have 4 edges.
But one of them is going into itself.
Exactly. And it's 1, 2, 3, 4. Can you see my pointer?
Oh, so that's over both of the, okay.
Yeah. So we have 4. If you look at this graph, it's something like this. 4 hands are coming out of it, coming out of the vertex. So
we're deciding the number of edges by how many lines are coming out of it or going into it or something, or like that.
Edges are basically the thing that connects to other lines. For example, here we have 1, 2, 3, 4.
Oh, I see.
So let's think of another problem. So let's go back to our first graph. So can you say how many ways I can connect these lines? So how many ways I can make this graph? Let's see, is it 4, 3, 4, 5, 6, 7, 8? Yeah. How many ways I can make this graph? In how many ways I can construct this graph? Like, for example, and how many ways I can construct this flower-like structure?
Is it some sort of combination?
Yeah, we need a combination. Very good. But let's say we pick this person. This person can connect to this person, and this person had 7 choices, right? So the first person has 7 choices. The second person has 5 choices, right? 1, 2, 3, 4, 5. 5 choices. This person has 3 choices, right? 1, 2, 3. It can either connect with this one or this one. So 3 choices. So 3. And the last one has just 1 choice, that person. So I can form this graph in how many ways?
There's a shorthand notation like 7 double factorial.
Exactly. Yeah, you can write it like this. Since it's a graph of valency 8, so you can write it like this: 7 double factorial. Or if you have n valencies are lines coming out of it. It's just n minus 1 double factorial. So number of ways we can construct this graph is n minus 1 double factorial. So if n equals 8, that is 8 is the valency, we have 7 double factorial, as one of you said, and so the number of ways is 105. 7 double factorial is 105. Is everyone okay with the combinatorics? Did you understand how the first person has 7 choices, the second person has 5 choices? This is just simple combinatorics. Yes, Shujosh.
So each line has only 2 choices. I mean, it's like we can't connect it. So, all right, I got it. So we can connect it with some other besides the 2 beside them, right? So let's say I want to connect the first one to the. If I want to connect the top one to the bottom one, it's possible.
Yeah, it's possible. It's definitely possible.
Yeah. Okay.
So let's look at another example. Let's say we have now, this was a 1 vertex scenario, right? So let's do some combinatorics with the second vertex example. That is, sorry, two vertices. Let's see an example with 2 vertices. So let's say it's a valency 4, 2 vertices of valency 4. So how many ways are there of contracting them into a graph? And I mean, you might understand from this, we will have multiple graphs. So in how many ways can someone say we can contract them? Okay.
Does one of them always have to connect to the other one?
Yes. So I'll give you a hint. Let's say I told you there are 3 types of graphs you can form with this. Can someone say, I mean, it's hard to describe a graph, but do you have any idea how the graphs might look like? This is simple combinatorics. Just think of it. What are the things that are allowed to do? What are we allowing the graphs to do? We can allow them to connect. For example, this graph, we are allowing them to connect with themselves, with one of its partners from the same vertex. We allow that. We also allow them to connect here with another vertex, lines of another vertex. So we are allowing basically 2 things. There are 2 possible scenarios. So can you tell me how many types of graphs I can generate with this? Okay. First, we can have self-contracted ones. That is, this, both of them contracts with one of its partner. That is, we are calling them partners if they're from the same vertex. So one possible scenario is this connects with this connects with this, or any possible way. We can have multiple of these graphs. And another one from this vertex would be this connects to this connects to this. So we have two of them. So if I write it like this, this is the figure 8. Did you guys understand what happened here?
Yeah.
If you're confused, you can ask me.
I'm actually pretty confused. Like, like the spokes that are coming out of the vertex, are those considered edges, or what are they?
Yeah, they are the edges.
Okay. So when we complete them, what do they become?
They become these figures. For example,
okay.
After contracting them, or after connecting the legs, let's call them legs. Let's call them legs. So after connecting the legs, or we can call them as particles, as you'll see in a bit. So after connecting the legs, let's say we connect the legs. For example, we can connect this leg with this leg, or we could just connect this leg with this leg, whatever way you want. So they're connecting with themselves. That is, this vertex, let's label it for your ease. Let's say this vertex is A, this is B. So A can connect with one of the legs of A, and B can also connect with one of the legs of B. Also, A can connect with one of the legs of B as well. So these are the things we are allowing A and B to do, or the graphs to do.
Do we allow connections to crisscross?
Yes, that is where the idea of maps come in. But
okay.
Okay, for now, let's say we allow everything. We allow everything now. So we allow the crisscrosses, everything. Those of you is there any of you who has done quantum field theory? Okay, no. So in physics, sometimes they're called the Feynman graphs, but we are dealing with a different problem. We are basically in the domain of graph theory. So we won't call them Feynman graphs, but these are basically graphs that we can, there are multiple types of graph scenarios that we can come up with. Okay, so this is one of the possible ways. Another possible way, can someone tell me another possible way? This is the self-contracted ones. Self-contracted ones. Or they're sometimes called disconnected because A and B are disconnected. A and B aren't related to, they're connecting one another. So what is another possible scenario? Another possible scenario, it has 4 legs, right? A can connect to itself, right? It can go to B as well. And B can also connect to itself. This is another possible scenario. And the third possible scenario is all of them are contracting. All of A is contracting with B, or is connecting with B. Think of them like holding hands. Like a person or someone has 4 hands, and another person has 4 hands, and you can join 2 of your hands, or you can join one hand with the other person who also has 4 hands. Think of it like this. So another possible scenario is all of the legs of A are connected to all the legs of B. These are the possible type of graphs we generate.
So can the edges like bend, kind of? Not sure if that's...
Yeah. You can have crisscrosses. As Saif said, you can have crisscrosses here. We're allowing that. So when I say these are only 3 types of graphs. You can have you can say, okay, bhai, you can have multiple graphs as well. For example, these two, one of them is this, another one is this. You can say that they're different, but I'm saying that they're the same kind of graphs. They connect with themselves.
I kind of want to know how they connect. Like,
Think of
I'm
it
not
like
sure
holding
how.
hands. Think of it like a person has 4 hands.
So the graphs don't have a specific structure. They're kind of like changeable.
They're just interested in holding hands. Think of it like this. They're interested in holding hands. A person with 4 hands, they're just interested in holding hands. And they can hold hands with themselves. They can hold hands with another person having 4 hands. That's basically it.
Okay.
I have a question. Like, I've seen graph theory from other places, and there are like these nodes and edges can only be between 2 nodes. But are these structures those things, or are these structures slightly different, or a generalization of that or something?
It's more of a generalization of that.
Okay.
These are simplest possible ways. You can have maps. When you go to maps, you'll understand. For example, the question you asked, the overlapping question, we will restrict that in maps. We won't allow maps. For example, the things we are calling maps, we won't allow the crisscrossing thing that you mentioned.
I see. All right.
Okay. So these are the 3 possible types of graphs we generate. So So how many of them we will have? Let's say of type 1, how many these disconnected graphs, we are calling them disconnected because their A is not connected to B. How many type of disconnected graphs will we have? Think of it. Like, for example, let's do the combinatorics again. These are the figure. It's very badly drawn, but okay. So the first person, again, can connect to 3 of them, right?
Yeah.
If you choose anyone, the other can connect to 3 of them. And if you connect it, the other person has only 1 choice. So it's just 3 double factorial. Same case here, 3 double factorial. So number of ways we can form this graph is just 3 double factorial squared, which is 9.
So the 2 graphs are distinguishable?
Yes.
Or not?
Yes. We are allowing them to be distinguishable. If we don't, we'll come to that. We'll come to that when we'll see a case where we can distinguish between them. Then you have to do some. I'm pretty sure you have done it. You divide by some number when you can't distinguish, right?
Mm-hmm. Yeah.
Like you have done all of you have done cup or combinatorics problem in high school. So you divide by a number or something to fix the overcounting issue. So now let's go to this is case 1, case 2. Okay. So can someone fix this combinatorics for me? Does any one of you have any idea how to fix this? Because there are 2 self-connected ones. That is this part, that is A connecting with A. And if we call this B, and we have 2 of them going out and matching with B. Okay. So
I think there is 2 possibilities.
Yes. Yes, Partho.
I think there are only 2 possible cases here, because A and B, both of them have to be connected to itself. So we don't count that. And
yeah, but you have, let's say you have 4 legs. think of it like this. There's 4 legs of this graph. There is you don't know which one of the twos are going to self-contract, right? So
yeah, that's right.
Any one of them can self-contract, and the other two has to go to B. Let's first fix the self-contracting issue first. So can you tell me how many of these self-contract? If you think of it, you have to choose 2, right? It's combinatorics, 4C2. If you're familiar with combinatorics, it's just 4C2. You have to just choose 2. So if I write this like this, it's in factorial. It's the combinatorics formula. So you're choosing 2. It's 2 factorial, and for each one of them, I have this number. So this number is squared. Now we have fixed the self-counting thing. Is every one of you okay with this number that I wrote?
Yeah, I think.
think of it.
Wouldn't it be 4C2 for the first one as well? Because you're again choosing 2 of them in example I. You're choosing 2 of them to connect to each other, and then you're choosing the 2 other ones to connect to each other. Is this to evaluate to like 3, like 4 factorial over 2 factorial, 2 factorial? Is this going to be 3 or something? Because
for example, no. It's a good question, but think of it like this. In the first one, all of them are self-contractions. Here, 2 of them are self-contraction. The other 2, we don't need the other 2. We need the other 2 we don't need the other 2 to self-contract. We need the other 2 to be free. But in the first case, or example I, or example 1, we didn't need that. We just needed all of them to self-contract.
Well, there are 3 ways for the first one and the second one to self-contract on 2 of the spokes, and then you have 4 spokes left to connect to each other. So it's again 9, isn't it? Mm-hmm. I guess you could flip-flop the second one, but then that would become 18. But
yeah, but basically they are doing the same thing. Like you're connecting them. You're talking about this, right?
I'm talking about number 2. Like in number 2, you have 2 objects. Both of them self-contract once. There are 3 ways to do both of them. So then you have 9, and then the remaining 4 spokes have to connect to each other, which you could flip them or you could not flip them. So that gives you 2 different ways.
Exactly. We'll come to that. We'll come to that. But first, we need to choose 2. Exactly. So as I've said, first, if we choose 2, it's 4C2. If we choose that, the next is it can connect to them like this, or we can invert this. So we have 2 of them. 2 ways of doing it. For example, it can connect like this. It's very hard to show it with. It's very easy to show with fingers, but as I'm not showing it with. Okay, there's 2 ways. One of them is like this.
You could color code them.
Yeah, let's do that. It's a good idea. One of them is this. The other one is, let's pick a different color, is this, right? 2 ways. So if you calculate this number, it's 72. And the third one, I need one of you to do it, and I'm surely not doing the combinatorics. One of you must do it for me. So any one of you.
4 factorial.
Sorry? Tanmay, you were right.
4 factorial.
Can you explain why 4?
If we take one vertex from, one leg from A,
exactly,
there are 3 ways to join it. 4 ways to join it. Exactly. For the next leg, there are 3 ways, then 2, then 1.
Exactly. Very good. This person has 4 options, as he said. The next person has 3 options, so it's just 4 factorial. If you sum this up, you'll get 105. Are you familiar with this number? Did we get this before?
So a graph with 8 lines is the same as 2 graphs with 4 each. Is that it?
Yes. So it's not surprising in the sense that we are just making a team here. Just like this guy, this is one team, and this is one team. But all we're doing is just,
you could like superimpose the 2 graphs and you'd get the same thing.
Exactly.
Right? Like you'd put a B on A and it would just be the 8-spoke graph.
Exactly. So it's not surprising in that sense, but yeah. So 105 ways. Okay. So still the same. So as I said, you can see them as particles that holds hands, a special kind of particle that holds hands. But let's say they are indistinguishable, that we don't know which one. For example, when we were selecting it, we would say this person is connecting to the other 4. But let's say we can't distinguish the particle. They're identical particles. So what do we have to do? For example,
we have to divide by the repetitions.
Exactly. For example, here, if it's the same, if you connect, okay, it's the same. All of them in different orders, they're the same. They're indistinguishable. So they're the same graphs. So we have
so then you have to count the number of ways you can get the same graph.
Yes. So I will give this to you as a brain teaser. The number we are dividing by.
26.
So
আমি বলছি একটা ফাইল না
Prama, you're not muted.
I think she has a question. Let me mute her. I think she has forgotten that we are. Okay. So for indistinguishable particles, let's say, for example, the example we did, A, B, self-contract. We could say A goes to B 2 times. If you're giving an input in a computer, if you wanted to say, if you develop a program that says A goes to B twice, and for example, you can have graphs with many vertices and many valencies, but it's easy to do for 8. They complicated stuff with them, but the analysis of this is easy, but computation is hard. So you can develop a program or some sort. So A goes to A and B goes to B. If you want to give an input to the computer, you can give it like this. So this is the indistinguishable case. What if they're indistinguishable? We have to divide by this number. For example, for the 8 valency case, we have to divide by 1/8 factorial to avoid overcounting. Why 1/8? This is your homework. This just think of it for 10-15 minutes, you'll understand. Or if you still face problem, just start with a graph that is, let's say, valency 2 or 4. Start with a very simple one. You'll understand why it's 1/8. So if you call them as particles, the number. So this is let me write it like this. Okay. So if you calculate this, this is 1 over 4 factorial. You can write it like this, and 2 to the 4. All we did is just divide by a number so that we don't have the overcounting problem. That is, we don't want to count graphs that are equivalent. We don't want to count them twice because, yeah. So we don't want to count configurations that are equivalent. So there is a beautiful interpretation of this number. So it's very interesting in quantum field. If any of you have done it, it's called the symmetry factor. But for us, this is just the symmetry of a graph. How? We'll see. So we have, let's say we have this graph with, so the number 2 to the power 4 is the flips. That is, if you flip it like this, if you flip the petals, you have two different orientations. You flip, but they are basically the same. You have the freedom to flip it in any direction you want. So, or like this, the directions have. So if you flip it like this, it's invariant. So the graph remains the same. It's the flip operation.
Does that mean that the graph is bidirectional?
What do you mean by bidirectional?
Like A to B is equivalent to B to A?
No, this is just a single. We are dealing with a single vertex graph.
Oh, okay.
8. So it's just, if you flip the petals, think of it like a petals of a flower. If you flip it, it's the same. Okay. It's one, this number, we'll see this in a bit. So this number has a beautiful interpretation. We'll see this. And the other number, 4 factorial, this is the flip. Like if you flip the petals, they're basically the same. And so, okay, you have 4 petals. You can order them in any way. So this 4 factorials is the petals being same. They're the same because they are, yeah, they come from indistinguishable particles being same. You can order them in any way. So 4 factorial comes from ordering petals. Like you have the freedom to order the petals in any way, and it will still give you the same graph. And even after the flipping, it will still give you the same graph. So this number, we'll call it, this is very bad drawing. Okay, so we will call this the automorphism factor, but sometimes in QFT, we call this the symmetry factor of the graph. So this is the automorphism factor, which is how many symmetries or how many things or how many operations I can do on this graph and still have my graph back or still have the same graph. So this number precisely tells me that. Are you okay with this number, or have I lost you?
Yeah, I got lost somewhere.
Okay, just if you're lost, just ask me.
I'll just go to the videos again, and yeah.
No, you can ask me. It's fine. You can ask me. Which part? The flipping part, or?
Well, yeah, after the flip, and I'm like, okay, what's going on now?
So
all the petals are identical, right? So,
yeah, that's what we're aiming for. That's the gist of it, right?
Yeah.
So like, even if you flip the petals, it's gonna look the same.
Yeah.
Okay.
And if you in a different order, for example, you have one order. For example, if you say, if you put this here, it's the same. So 4 factorial ways of arranging them, right? You have 4 factorial configurations. Just think of it like, however I arrange the petals, we are talking about the petals themselves. However I arrange them, they give me the same graph.
Okay.
You can order them. That's where the 4 factorial comes into play. And 2 factorial is just the flip. 2 to the power 4 is just the flip. You have 2 operations for each of them, and 4 of them. You have 4 of them. So 2 into 2 into 2 into 2. Right?
Yeah.
Okay.
Yeah, I got it now. Thanks.
No problem. You can just, you can ask me anytime and just interrupt me. This is the purpose of the live session is to have an interactive discussion. A lot of things will not be clear from my end, but this is important because if you understand this, when we will be doing ribbon graphs, this is an alternative approach. When we will be doing the more formal approach from, let's say, Saturday, we'll have one more class before Saturday. And when we do the more formal approach, you'll understand the physical, intuitive picture of what's going on. Okay. So this number is, again, the symmetries of the graph, or in how many ways I can order my graph and still get, how many operations I can perform of the graph and still get my graph back. Yeah. So let's see what kind of numbers we would generate for the previous example. Let's say for this example, we have 9 of these, right? Okay, I forgot to mention one thing. Let me mention that. So coming back here, 1/8 factorial, that is, we put that due to the particle indistinguishability. That is, we wanted the particle indistinguishability, in the sense that since they are indistinguishable, they give me the same structure. So in the sense, we have converted the particle indistinguishability into a symmetry of the graph. That is the symmetry of this graph. Right? On the right-hand side, we sort of have a symmetry. That is symmetry in the sense they're the same. We can perform a flip operation. We can perform ordering of petals. And that would make my graph, leave my graph unchanged.
Okay, I have one confusion.
Yeah.
So how does this flower-like graph connects to that? I mean, like the second type of graph we discussed. Is it connected to that, or is it's just a separate example?
For now, it's a separate example. It's a one-vertex graph, and for example, this one, this one is a one-vertex graph. This one is a which one? Yeah, these are two-vertex graph. So they are separate examples, but again, they give you the same number. So hold on to that thought.
Another thing is, why did you divide by the symmetry? Yeah, no, the last example. I mean, why did you divide by 4 factorial into 2 to the power 4?
Oh, this is the number I get. If you calculate this, you'll get this. I wrote an equal sign here. If you multiply this with 105, you get this number. And interestingly, this number turns out to be the symmetry of the graph. This is the interesting part. Like, you're doing some indistinguishability things. And when you do that, what you come up with is that the symmetries of the graph, or the operations that leave your graph invariant. That is the interesting part.
So do we define the symmetry of the graph by like 1 over the times of operation that can leave
Exactly.
the
Yeah, that is your symmetry factor. The operations, basically automorphism factor or the symmetry factor, these are the operations that leave your graph invariant. And surprisingly, you are generating these numbers just by considering indistinguishable particles. So that's the interesting thing to notice. So sort of like particle indistinguishability, let me write this up. Graph symmetries. And by particle, we mean again the legs particles that hold hands, or a special kind of particles. Okay, so let's see what kind of numbers we generate for, let's say, the previous example, which is this. Since we are talking about symmetries, yeah. Okay, can someone tell me this number? What are the operations that we can come up with that would leave my graph invariant?
It should be 2 squared times 2 factorial to the power and that thing whole squared.
You're close. You're very close. You're very, very close. Okay, let's see. Let's start with the left side. So we said the particle indistinguishability is converted to my graph symmetry. That is the things that make my graph invariant under a change, or yeah, that gives us freedom to do various operations on the graph. So we multiplied by 1/8 factorial here because there are 8 indistinguishable particles. What number do we multiply here? So there are indistinguishable particles inside each vertex. You have 2 vertex. Yeah, combinator. Yeah, you might be confused regarding all the combinatorics at play. Just think of it. You have a vertex. And you have 4 particles here. And you can't distinguish them. So what is the number I should divide by in the particle in this side? You have 4 particles. Again, you have 4 particles.
Yeah, I think it should be 2 squared times 2 factorial.
It's 4 factorial. Remember, I got 8 factorial here. It's just 4 factorial. And since we have 2 of them, 8 factorial squared. Are you confused why it's 4 factorial squared? There are 4 particles. Think of it like this. There are 4 particles. We can't distinguish them. So divide by 4 factorial squared for each of them. So, sorry, divide by 4 factorial. And for this one, we get 4 factorial. For this one, we get 4 factorial. Right? 4 indistinguishable particles. That's why 4 factorial. And since they're indistinguishable as a pair, like you don't know which pair, let's say if this was A and B, you don't know which pair is A and which pair is B. So times 2. Okay, I expect you to ask me questions because
What are we counting?
Some of you might be confused. Sorry?
What are we counting actually?
Think of it like this. 4 indistinguishable particles. that is 4 indistinguishable legs, right? So we divide
Why
by
are we
4.
calling legs as particles?
You can call it various things. Legs, particles, it's the same. Particles that holds hands. It's just a way of saying it. Or legs that connect to each other. Legs that connect to other legs. That is the basic idea. That is the basic notion of why we talked about. Yeah, that is the basic notion of why we first talked about graphs that connect with each other, or let's say here, graphs that connect with each other and with other vertex graphs. These are the legs or particles that holds hands, or whatever you want to call them. You can call them in any way you want. But one of the features is it connects with various graphs. And yeah. So you get a 4 factorial from each, because these are 4 indistinguishable particles or legs. So 4 factorial, we have squared because each of them are coming from 4 factorial. Each of them. So for each of them, we have 4 factorial. And that's why it's squared. And as a pair, this is a pair of graphs. As a pair, it's also indistinguishable. We don't know, because again, think of it like 4 copies of yourself. We don't know how to distinguish them, but basically you are the same. So for each of them, we divide by 4 factorial. So 4 factorial squared, and as a pair, there is an indistinguishable. I don't know which pair is standing first, which pair is standing second. As a pair, they're indistinguishable. That's why multiplied by 2. So if you multiply this with 9, because we have 9 of these, as you know, so we get this number. So what are these? So particle indistinguishability, we were talking about particle indistinguishability here. That is what happens if we can distinguish the particle. And on the right side, we have the symmetry factor. So what symmetry factor corresponds to this graph? What are the symmetries? What are the things that will keep my graph invariant? That is, what is this number? What is this number? Okay, if I tell you that I can do these operations, what are them? They are, for example, flips again. You can flip it like this. You can flip this like this, and you can up and down. So you have 2 ways here, 2 ways, 2 ways, and here 2 ways. So it's 2 cubed. That's where my 2 cube comes from. And since we have 2 of them, so 2 cubed square, and again, we can organize the graphs however we want. This can be first, this one can be first, or this one can be first. So that's where this 2 comes from. Okay. If you're confused, you can ask me questions, because I want you to ask me questions. Tell me where I have lost you. Then we can discuss. So let's make this an interactive session. If you're lost, let's get back to me again. I'll repeat. Yeah.
I have a question. Like, when you said that the indistinguishable particles give you 4 factorial,
Yes.
what are we counting to get the 4 factorial? Like, are we rotating the particles around, and there are 4 factorial ways to rotate them or something?
think of it like this. There are four particles, and they're indistinguishable.
Like what operation over are they indistinguishable? We like moving them or rotating them? What?
Whatever you do, they're indistinguishable. You can distinguish between the four. For example, you have 4 electrons. You can distinguish between the 4 electrons you possess, right?
I think it's something like permutation, right?
Sorry?
Is it something like permutation, like what we do?
Yes. Okay. For now, just try to get hold. When you see this video again, you will try to understand this. Or if you still don't, I'll get back to you. But for now, try to understand the symmetry factors. This is more important. The particle indistinguishability, that's later. But try to understand the symmetry factors. Did you understand why we have a 2 cubed here?
Yeah.
Yeah, I got this version.
Yeah. Try to understand the symmetry factor first. That's more important. If you're still confused, we'll get back to that later. But yeah, we have a lot to cover. So, but the most important part is just try to understand the symmetry factor. You have 2 cube ways, 2 graphs. So 2 cubed squared, and the way you arrange them, it doesn't matter. So as we are interested, for example, for those of you who have done statistical mechanics, you know, we sum over possible configurations, or let's say in path integrals, you sum over possible ways of doing them, or we want, in our case, we want a function that generates this kind of graphs. Let's say I want to generate a 4 vertex graph. I want a function that does this job for me. So we will call this our generating function, or you can call this partition function as well. So let's make a definition. We'll call this partition function, or a generating function. It's better to call partition function because we'll see that generating functions, and sometimes we call a different thing generating function, but you can call this that it's a generating function for our graph. So let's denote it by Z, and let's say we want a function. Think of it like this. We want a function that gives us graphs of valency 4. Let's say because we were dealing with valency 4 graphs, that is like this. This is one example for valency. So we want to generate graphs, or we want a function that gives us these graphs of valency 4 and n vertices. So this function is basically a sum over those possible graphs. Let's define a number gn times they're weighted by our automorphism factor. So what is this number gn? For example, g0 would correspond to a vertex 0 graph. G1 means you have vertex 1. G2 means you have 2 vertex. And G10 means you have 10 vertices, like this. Okay, so this is our function which generates our required graph. So if we start summing over, we'll see that 1 plus G1, so it's just G. And what is the 1 vertex graph? What is the graph that you get in, let's say, if you have 1 vertex and a valency 4? Can somebody tell me? Let's say you have valency 4, that is 4 particles or 4 legs coming out of it, whatever you want to call them. And what is the graph we have at vertex 1? at vertex 1, we have this graph, that is, all of them self-contracts like this. You can think of it like this. And what is the symmetry factor of this graph? What is the symmetry factor of this graph? Can someone tell me? You should be able to tell me this.
2 cube.
Yes. Tanmoy, what were you saying? I heard Partha's answer. Is it the same?
I said 2 cube.
Oh, okay. Yes, it's 2 cube. So this number is 2 cubed. Why? Flip, flip, up and down. So what kind of graphs do we have at order g squared? Can you tell me what kind of graphs we can have at order g squared? I did it.
With symmetry factor 1 by 2 into 2 cube whole square.
মানে গ্রাফ কিরকম হবে এটা জিজ্ঞেস করছে, মানে কি কি গ্রাফ পাবো? একটা হচ্ছে সেলফ কানেক্টেড ওয়ান্স, ডিসকানেক্টেড, right? Duta vertex, remember 2 vertex and valency 4. You had this person, and you had 1, 2, 3, 4. Right? One of them is connecting, all of them self-contracting, two of them self-contracting, and 2 of them connecting to the other, and the third one, and so on. We can have g cube. At order g cube, we will have 3 vertices. At order g10, we'll have 10 vertices, and we will have different graphs corresponding to it. Are you okay with is everyone okay with our function that we wrote here?
Yeah.
Shujosh, Saif, are you guys lost?
I'm somehow keeping up.
I think I'm all right.
Yeah.
So you understand how this graph works, right? How we're defining this function that generates my graphs.
G is just going to give us a magical number related to each graph, right? Like we're not really bothered about how it gets the number.
No, the power of G tells me how many vertex is there. For example, G squared, there are 2 vertices.
Okay.
G1, 1 vertex. G cubed will have
G cube 3 vertices, yeah.
Yes. And what will my numbers give me? For example, what will this give me?
This is the symmetry.
No. The automorphism factor. You understood how we get the symmetry factor of 1 over 2 cubed, right?
Yeah.
Okay, good.
Does G give you a number, or what does it result in? Like,
G is just a constant which helps me count the number of vertices corresponding. Okay. For example, the coefficient of G square will tell me how many different types of diagrams I have. Let's say self-connected ones, or these ones, or these ones. It just keeps me. It just keeps track of the number of vertices.
I see. Okay.
It's just a constant that keeps the number of vertices, that keeps track of the number of vertices. For example, G1, 1 vertex, G2, 2 vertex, G cube, 3 vertex. And the symmetry factor tells me how many of these things I have. For example, this I have.
So the 1 at the beginning is because there's only one way to do a G0 graph. Is that right?
Yeah. I mean, there's no vertex.
Yeah.
Okay. One homework for you would be, try to do this, because otherwise it won't help you much if you don't try it yourself. Everything is just about trying yourself. Let's say find these symmetry factors. For example, find what will be in this place, or in this place, or in this place. Find these things. And let's say, yes, someone had a question.
Oh, sorry, I have a question.
Yes.
Is this partition function is, I mean, I think it's related, but I mean, do you know what's the relation between the partition function we use in quantum field theory and the one you have just written?
It's yeah, you'll see this in a bit. It's, for example, you generate connected graphs and disconnected graphs using path integrals, right?
Mm-hmm.
I'll define this in a bit, but because this is, we are not doing quantum field theory, we are just calling them graphs. But this is basically a quantum field theory, and these are Feynman diagrams. These are bubble diagrams.
And so is this partition function convergent in this simple example? Or it's just a formal summation?
It's just a formal summation. We're not thinking about the convergence in that sense, but it's just a summation of your possible graphs you can have.
Okay, and so
of course you can do a convergent analysis, but no. I don't think they are convergent. Okay, and like
so the partition function we use in statistical mechanics or quantum field theory is a special case of this definition, right?
Yes.
Because these graphs are more general than Feynman diagrams.
Yeah, these graphs are more general than Feynman diagrams.
Okay, yeah, thank you.
Yeah, no problem. Okay.
Okay, I have a question. Does n run up to infinity?
Yes. In this sense, you can have a lot of vertices. If you're naively thinking, you can have infinite number of vertices. Because I want this function to carry every vertex I have at hand. I want this function to be like all-knowing function, sort of like a God function, which knows to generate all possible graphs we want. So these graphs gives us, did someone have a question?
I have another question. Just do you sum up all the symmetry factors for different graphs on this when we have to calculate this line?
Yes. For example, if you sum this up, you'll see what you get. For example, for the first case, the homeworks I gave you all is just this number. I think I've calculated it here. Did I? Yes. So everyone will have a symmetry factor. So the coefficient of G squared will be just a sum of these numbers.
Okay. I was confused if it was something like I multiply the symmetry operations. I mean, I add the symmetry operation first and then divide by it, or I just sum up the symmetry factors of separate kind of graphs. Okay, I got it.
Yeah. For example, you don't need to think if you know the graphs. For example, now we have come a long way. For example, at order, let's say G squared or G cubed, you don't need to take into consideration the particle indistinguishability or things like that. If you know what kind of graphs you generate or how many of them you have, you can form these graphs and if you can look at them and just calculate the symmetry factor, and then you know everything at what happened of that. I mean, you know the symmetry factor at order G cubed or say G4. You don't need to go into that analysis. You'll just understand what's the coefficient of G squared. Okay, so the main point is this is a function. This function that I defined here. It gives me my desired graphs of valency 4 and any number of vertices. We want the fifth vertex. It's all contained in this function. Everything, 5, 10, 50, whatever vertex you name, it's all contained in this powerful function. Okay, so now I make a claim. So I claim also notice in the sum of graphs, we can have disconnected ones, right? This is a disconnected graph. That is, in the sense, if this is a vertex isn't connected with another vertex in this graph, but here it's not disconnected. The vertices are connected, like they're talking to each other or something. So this is a disconnected graph. So I claim that the function I defined, this one, I can generate them, or I can get the same thing from this function. This is the partition function. This is a function we call free energy, but I'll tell you its job. It's connected. It's a function, or it's a function of connected graphs. What do I mean by that? It's minus is just a convention. Connected graphs. So basically what I am saying is, what I claim is, I can generate disconnected graphs and all possible kind of graphs just from connected ones. This is what I'm claiming. Is everybody okay with the function f? The function f is a sum of connected graphs. If I write it out, it's something like this. G over 8, it's the first one, the connected one, and it's the order G squared. You have this, and okay, 2 over 10. So this is the function of connected graphs, and so on. So what I am claiming is, with a function of connected graphs, there is a function f that has all the connected graphs in it. I can get an actual graph function, that is, which generates all kinds of graphs, disconnected ones, connected ones, with just connected graphs. This is what I claim, which I will show this in a bit. Is everybody okay with the definition of f?
Yeah, okay.
Yeah, okay.
Let me get something straight. Like z is the function of all of the types of graphs, right? Including the disconnected,
everything.
And then f is a subset of that. But if you take e to the power minus f, then you get all of them.
Yes, that's what I'm claiming.
Okay.
Can someone tell me intuitively why this should be the case?
I guess you could have two connected graphs next to each other to make a disconnected graph. So that
yes.
kind of...
Of course. Yes, you're right. Yes. For example, if we do this, what happens? The first is minus f squared over 2, and so on. Let's just not bother with higher order terms. First is 1 plus this, right? G over 8. Let me draw the figure as well. Then it will be easier for you to visualize. Now, what happens at order G squared? F is this, and order G squared, I can straight say that I have this plus this.
Should the function should be e to the power minus gf? Like we're putting vectors here.
G is already there.
Oh, yeah.
In the definition of F, yeah. So I get this graph. Can someone say how I get this graph? From which term? You have 3 terms. And from one term, I get this disconnected graph. Which is the term? This is my F squared term. Think of it like this. If I have the F term, if I square it, I have G squared and 2 of this, right? Right? Are you guys still confused?
I'm not exactly sure how the addition of 2 of these works, but I guess it makes sense.
Yes. If you squared them, for example, if you square this, you get 2 of these, right? If you square our F, you get 2 of these and G squared. So basically, what have we done? We have gotten a disconnected graph at G squared from connected ones. At all orders, it's true. You can check at, let's say, G cubed. Let's give you another homework. Check at G cubed. It holds. This holds at all orders. So yeah. So we have basically, what have we done? We have generated disconnected graphs and all graphs just from connected ones. If we have the connected graphs, we can generate the disconnected ones using this. Okay. Okay. Do you guys want me to stop here, or do you guys want? Depends on you. Or do you guys want the other things in next class?
Like, isn't this supposed to be like a 3-hour class, or I don't know?
It's supposed to be long as you can take it.
Okay.
If it's already too much, which seems like, then I can stop. But if it's not, I can continue for, let's say, half an hour and finish the things that I was planning to cover. Tell me, be honest, it's fine.
Well, I personally think I can at least go for half an hour, but I guess 5 to 10 minutes break would be a good idea.
Okay. Do you guys
if you want to go further.
Yeah, I have no problem if you continue.
Well, I'm fine with the continuation as well.
How about this? I planned to go a long time. How about we have just 20 minutes and just a 20-minute more, then I can finish what I wanted. I can finish just a part of what I wanted to finish. Or is this a good place to stop? Okay, yeah, it's a good place to stop. Because the other things, they need a bit more time, but yeah. Just for now, okay, let's stop here. But the things you need to know is just try to get hold of this combinatorics at hand and try to understand the connected things and disconnected graphs and all those symmetry factors. Try to do the problems that I gave as homeworks. Try to draw the graphs yourself. They're interesting because if you say in how many ways I can pair them up, they're interesting problems. And it's more of a visual problem of understand. If you're doing it from an intuitive perspective, it's more of a visual problem. So try to understand that. And in the next class, we will try to cover more things.
I have a question.
Yes.
So like we defined Z to be in a particular way, but what is the significance of it?
Okay, let's stop the recording so that and I'll answer your question in a bit.